There is a world in our solar system where the wind never stops, where the atmosphere is not a gentle blanket of warmth and oxygen, but a weapon, a planetary-scale machine of destruction spinning at speeds that have no equivalent on Earth. No storm, no hurricane, no force we have ever experienced in the entire history of human civilization comes close to what moves on that world every single second of every single day. That world is Neptune, and if you were transported there, right now, this instant, you would not have time to be afraid. You would not have time to breathe. You would be gone before your mind registered what was happening. The winds on Neptune travel at 2,100 miles per hour. Let that number settle. 2,100 miles per hour. The fastest military jet ever built by human hands. The SR-71 Blackbird, a machine of titanium and fury designed specifically to escape what chased it, flew at 2,200 miles per hour at absolute maximum velocity, burning fuel at catastrophic rates, pushing its airframe to the edge of molecular coherence. And that machine required over a decade of secret engineering, the combined intellectual force of thousands of aerospace minds, and a perfectly controlled atmosphere just to exist. On Neptune, that speed is the wind. That is not a peak gust recorded once in a century. That is not the eye wall of the most violent cyclone ever measured. That is the ambient velocity of the upper atmosphere, constant, merciless, and indifferent to the concept of survival. Nothing on Earth prepares you for this. Not Typhoon Tip, the largest tropical cyclone ever recorded, with sustained winds of 190 miles per hour that obliterated islands and terrified meteorologists. Not the highest wind speed ever measured on the surface of this planet. 253 miles per hour during Cyclone Olivia in 1996. A reading so extreme that scientists questioned their instruments before accepting the truth. Neptune doesn't question anything. It simply moves, and the scale of that movement, the sheer, unprocessable enormity of what is happening on that blue giant 4 billion miles from where you are sitting right now, requires us to do something uncomfortable. It requires us to abandon every instinct we have developed about what a planet is, what an atmosphere does, and what the word weather means. Because what Neptune does is not weather. It is something else entirely. Imagine standing on a coastline during a Category 5 hurricane. The sound alone is enough to trigger something primal in the human nervous system. A vibration that bypasses reason and speaks directly to the oldest part of the brain, the part that has known danger for 300 million years of vertebrate evolution. You feel the pressure differential in your chest. The air tastes electric. Every cell in your body is screaming one word: run, now. Multiply that wind speed by 11. 11 times. That is Neptune's atmosphere on a quiet day. And Neptune does not have quiet days. What you would experience if somehow transported to its cloud tops would not register as wind in any way your nervous system could categorize. At 2,100 miles per hour, air ceases to behave like a gas you can push through. It becomes, for all practical purposes, a wall. A transparent, invisible, absolute wall traveling at supersonic velocity. And it would strip the molecular bonds from every structure you have ever built, loved, or depended upon in milliseconds. Concrete, steel, titanium, carbon fiber, the hardest materials we assemble with our most sophisticated manufacturing, would not resist. They would not bend dramatically. They would not shatter in a cinematic explosion of debris. They would simply cease to maintain their form. The aerodynamic forces at that velocity don't destroy things the way we imagine destruction. They disintegrate them. They reduce solid matter to powder and scatter that powder across thousands of miles of frozen, impossibly dark atmospheric bands before anything has had the chance to fall. A city would become a memory in under a second. Not a ruin, not a wreckage field, a memory. And here is the part that should silence you. The part that even planetary scientists pause on when they let themselves truly consider it. Neptune is not a rogue object. It is not an anomaly from outside our solar system. It is not a cosmic intruder with alien physics. It formed from the same cloud of gas and dust that formed Earth. The same primordial nebula, the same solar winds, the same gravitational collapses and accretions and billiard ball collisions of planetesimals that eventually produced oceans and continents and oxygen, and you also produced that. Our family includes a monster, and we are only now beginning to understand what kind of monster it truly is. To understand Neptune's winds, you must first understand what wind actually is. Not the poetic version, not the breeze through autumn leaves or the salt-heavy gust off a morning coastline. The physics, the raw, unromantic mechanism underneath every movement of air that has ever touched your skin. Wind is the atmosphere moving from high pressure to low pressure. That is it. That is the entire engine. A region of gas gets compressed by heat, by rotation, by the geography of the surface beneath it. And the surrounding gas rushes in to equalize the imbalance. The steeper the pressure gradient, the faster the rush. Every gale, every trade wind, every Category 5 hurricane that has ever torn a coastline apart is nothing more than the atmosphere attempting to reach equilibrium, trying to balance itself, trying to find peace. Earth's atmosphere is restless, but it is not insane. Neptune's atmosphere has abandoned the concept of equilibrium entirely. And to understand why, truly understand it, not just accept it as a data point, you have to look at where Neptune sits in the architecture of our solar system and confront something that overturns a deeply human assumption about the relationship between distance and energy. We assume that the farther you are from the sun, the colder and calmer a world becomes. It is an intuitive assumption. It is a reasonable assumption. It is wrong. Neptune receives roughly 900 times less solar energy per square meter than Earth does. 900 times less heat striking its upper atmosphere every second. By every intuitive model we carry in our heads, Neptune should be a still, frozen, barely breathing world. A dark cathedral of cold where nothing moves with any urgency because nothing has the energy to do so. Instead, it has the fastest winds in the solar system. The contradiction is not subtle. It is not a minor deviation from the expected. It is a full, categorical reversal of everything a reasonable mind would predict. And it forced planetary scientists to dismantle assumptions that had been embedded in atmospheric models for decades. Here is the truth that emerges from that dismantling. Neptune generates its own heat, deep inside that blue globe, beneath the visible methane clouds, beneath the layers of compressed hydrogen and helium, beneath regions where pressure climbs to conditions that make the deepest point of Earth's ocean feel like standing in open air. Something is radiating. Neptune emits approximately 2.6 times more energy than it receives from the sun. It is not a passive body warmed from outside. It is an active machine. still releasing the gravitational energy locked inside it during its formation 4.5 billion years ago. The sun's heat shapes Earth's weather from above. Neptune's internal heat drives its atmosphere from below, and that distinction changes everything. Because when heat rises from beneath a rotating planetary atmosphere with no solid surface to create friction, with no mountains to break flow, with no oceans to absorb energy, with no geography whatsoever to interrupt the momentum of moving gas, the atmosphere does not dissipate that energy. It organizes it. It channels it. It builds and builds and builds until what began as a pressure differential becomes a river of atmosphere, moving at velocities that feel more appropriate to a spacecraft than to weather. Think of what friction does on Earth. Every wind that races across the surface of this planet eventually meets resistance. It drags across grasslands, crashes into mountain ranges, churns against the surface of the ocean, and transfers energy into waves. Friction is the atmosphere's constant opponent. The invisible hand that bleeds velocity from every storm system, that slows every jet stream, that eventually brings even the most powerful hurricane to a halt when it makes landfall and loses its energetic source. Neptune has no landfall. There is no surface to absorb the momentum, no mountain range to shatter a storm system into smaller eddies of decreasing power. The atmosphere of Neptune extends downward into increasing pressure and temperature until the concept of gas and liquid begins to blur and eventually dissolves into a superheated ionic ocean of water, ammonia, and methane that we call an ice giant's mantle. A substance that has no real equivalent on Earth, neither fully liquid nor fully solid, conducting electricity like a metal and flowing like a liquid under pressures measured in millions of atmospheres. Above that alien interior, the winds run free, unchecked, unburdened, perpetual. The great dark storms that erupt in Neptune's atmosphere. Systems comparable in scale to the entire surface area of Earth, form and dissolve and reform on timescales of years, not centuries. The most famous, observed by Voyager 2 during humanity's only direct encounter with Neptune in 1989, was a vortex so vast it was named the Great Dark Spot. A storm the size of our entire planet, gone by the time the Hubble Space Telescope looked for it 5 years later. Not because it weakened, not because it died, because it moved, restructured, and reassembled somewhere else in that churning blue void. The atmosphere of Neptune does not preserve storms. It consumes them and creates new ones, endlessly, without memory of what came before. There is something philosophically devastating in that image. Something that reaches beyond planetary science and touches the part of us that needs things to persist. Humans build monuments. We carve names into stone. We construct civilizations specifically designed to outlast the individuals who imagined them. Pyramids and cathedrals and digital archives reaching terabytes into the future. All of it driven by the same primal refusal to disappear without a trace. Neptune erases a structure the size of Earth in 5 years. Not through violence, through simple, patient, indifferent motion. And the winds are the instrument of that erasure. 2,100 miles per hour is not just a number describing velocity. It is a number describing what happens when a planetary atmosphere is freed from every constraint that makes weather on Earth recognizable and survivable. It is what emerges when gravity holds gas to a world. Internal heat drives it into constant motion. Rotation stretches that motion into powerful lateral bands. And there is nothing, not a single rock, not a single shoreline, not a single blade of grass, to say, stop here. The winds do not stop. They have not stopped for billions of years. They were moving at hypersonic velocity before the first single-celled organism divided in Earth's primordial ocean. They were tearing across those blue cloud bands before the dinosaurs existed, before the Cambrian explosion of complex life, before the first multicellular creature reached towards sunlight in a shallow Precambrian sea. The entire 4 billion-year epic of life on Earth. Every extinction, every adaptation, every evolutionary leap that eventually produced hands capable of writing and minds capable of asking why, happened while Neptune's winds moved without interruption at speeds our fastest machines have only barely equaled for seconds at a time. This is what permanence looks like at planetary scale. Not stone, not steel. Moving air, the methane in Neptune's upper atmosphere, is what gives it that extraordinary, deep, saturated blue. A color so pure and vivid that it seems almost artificial, almost designed, like a painter's deliberate choice rather than the byproduct of photochemical processes operating on a world of frozen gas. From a distance, it is beautiful in a way that the word beautiful genuinely fails to capture. It looks peaceful, serene. It looks like a place you might want to approach. That is the oldest trap in the universe. Beauty with no regard for your survival. The most lethal environments in the cosmos do not announce themselves with ugliness. They arrive wearing the deep, saturated blue of a cloudless sky on the most perfect afternoon of your life. And embedded inside that beauty, invisible and absolute, 2,100 miles per hour of wind is waiting, without patience and without mercy, for something to destroy. Let us do something uncomfortable. Let us place Earth inside Neptune's atmosphere and watch what happens, not as metaphor, not as creative license, as a precise, physics-based exercise in scale and consequence. Because the only way to truly absorb what Neptune's winds mean is to measure them against the thing you know best, the thing you live on, the thing every human being who has ever existed has called home. Earth's diameter is approximately 7,900 miles. Neptune's diameter is approximately 30,500 miles. Neptune is not a slightly larger planet. It is not the next size up in some orderly celestial catalog. It is a world so much larger than Earth that if you hollowed it out and tried to fill it with copies of our planet, you could fit 57 Earths inside its volume before running out of room. 57. The number feels abstract until you try to visualize it. Until you try to imagine stacking 57 versions of every ocean, every mountain range, every continent, every city ever built by human hands, every forest that has ever grown and burned and grown again, inside a single sphere. And all of that volume is atmosphere. Neptune has no confirmed solid surface. What it has instead is a gradual, terrifying transition. A descent through layers of increasing pressure and temperature where gas slowly becomes something that is no longer gas, where the boundary between atmosphere and interior dissolves into a mathematical gradient rather than a clean line. The cloud tops we observe, the blue methane bands that give Neptune its extraordinary color, are simply the outermost visible layer of a planetary interior that is essentially all atmosphere, all the way down, which means there is no ground to stop you. If somehow you fell into Neptune, if some impossible mechanism deposited you at the top of those cloud bands and gravity took over, you would not fall toward a surface. You would fall into increasing pressure, increasing temperature, increasing density, until the atmosphere around you compressed into something indistinguishable from liquid. And the distinction between falling and drowning became irrelevant. but you would not survive the winds long enough to fall. At 2,100 miles per hour, the dynamic pressure exerted on any object is not measured in the units we use for earthly storms. We describe hurricane wind pressure in pounds per square foot. A Category 5 hurricane exerts roughly 150 pounds per square foot on a structure, enough to peel roofs and collapse walls and drive wooden planks through concrete blocks like nails through paper. Engineers design buildings around these numbers. They run simulations, build scale models, stress test materials to their fracture points. At Neptune's wind speeds, the dynamic pressure on a human body would exceed 40,000 pounds per square foot. 40,000. The engineering analogy collapses at that number because no engineering exists to address it. The strongest materials humanity has ever manufactured: carbon nanotube composites, tungsten carbide, aerogel reinforced ceramics developed for hypersonic vehicle thermal protection, have tensile and compressive limits that Neptune's winds exceed by orders of magnitude. You cannot build your way through this. You cannot engineer a solution. The physics of molecular bonding at those dynamic pressures simply does not permit structures to remain structures. Matter has opinions about this, and Neptune's winds override every one of them. But the destruction is not random. It is not chaotic in the way a bomb is chaotic, spraying fragments outward in all directions with democratic indifference. Neptune's atmospheric bands are organized. They run in parallel belts of alternating direction, some moving eastward, some moving westward, creating zones of catastrophic shear where adjacent rivers of atmosphere traveling in opposite directions grind against each other at differential speeds that would reduce anything caught between them to a dispersed molecular fog within fractions of a second. Imagine standing between two highways where traffic is moving in opposite directions at 2,000 miles per hour, separated not by a median strip, but by nothing, by the sheer violence of adjacent airflows colliding at their boundaries. That shear zone is where storms form on Neptune. That is where the great dark spot was born. That is where atmospheric energy, unable to equalize, unable to find relief, concentrates into rotating vortices of such magnitude that they dwarf entire planets. We call them storms because we have no better word. But calling Neptune's vortices storms is like calling the Pacific Ocean a puddle. The word exists on the right conceptual shelf, but it fails catastrophically at conveying scale. Now consider what those winds would do to Earth specifically. Not to a hypothetical human body floating in Neptune's atmosphere, but to our planet as a geological and atmospheric object placed inside that environment. Earth's own atmosphere would be the first casualty. Our atmospheric pressure at sea level is 14.7 pounds per square inch, a delicate, precise equilibrium maintained by gravity and the thermal structure of our stratosphere. That equilibrium took billions of years to develop. It survived asteroid impacts, volcanic supereruptions, the great oxidation event that transformed the entire chemical composition of our air, snowball Earth glaciations that locked the planet in ice from pole to equator. Our atmosphere is, in geological terms, one of the most resilient systems that has ever existed. Neptune's winds would strip it in hours. The process has a name: atmospheric erosion by dynamic ram pressure. The same mechanism that has slowly stripped Mars of the thick atmosphere it once possessed. Though in Mars's case, the culprit was solar wind, moving at a comparatively modest 1 million miles per hour. And the process took hundreds of millions of years. Neptune's winds, acting on Earth's atmospheric envelope from all directions simultaneously, would compress and shear and accelerate our atmospheric layers beyond their capacity to remain gravitationally bound to the planet's surface. The stratosphere would go first, that thin, cold layer of ozone and nitrogen that absorbs the ultraviolet radiation that would otherwise render Earth's surface sterile. Then the troposphere, where all of Earth's weather lives, where every cloud that has ever formed over every ocean or mountain or desert plain exists in a layer only 12 kilometers thick. A layer so thin relative to Earth's diameter that if you scaled our planet to the size of a basketball, the troposphere would be thinner than a coat of paint. Gone. Not gradually. Not in the drawn-out geological time frame of Martian atmospheric loss. Gone in the accelerating cascade of a system that has passed its tipping point, where each layer of atmosphere stripped away reduces the gravitational retention capacity of what remains, which accelerates the stripping of the next layer, which reduces retention further, in a feedback loop that ends only when there is nothing left to strip. And then the surface. Without atmospheric pressure, Earth's liquid water, every ocean, every lake, every river, every aquifer beneath every continent, would begin to boil at ambient temperatures. Not because it has become hotter, because the pressure that keeps liquid water liquid at temperatures above its vacuum boiling point has been removed. The oceans would not drain. They would vaporize. They would lift off the surface of the planet in a planetary scale eruption of steam and be immediately captured by Neptune's atmospheric flows and dispersed across thousands of miles of churning blue bands, indistinguishable from the water ice particles already suspended in Neptune's own cloud layers. Earth's oceans dissolved into Neptune's clouds. The continental surfaces, now exposed to direct ram pressure from hypersonic atmospheric flows with no protective envelope to buffer them, would begin to erode at rates that make geological erosion look like the movement of a clock's hour hand. Rock is not infinitely hard. Granite and basalt have yield strengths, and those yield strengths have limits, and Neptune's winds exceed those limits the way a freight train exceeds the limits of a paper wall. The Himalayas would be gone. Not worn down, gone. What took tectonic forces 50 million years to push toward the sky would be reduced to suspended particulate matter in Neptune's atmosphere in a time frame too short to deserve the name. This is not catastrophe as humans understand catastrophe. Catastrophe, in the human vocabulary, implies aftermath, ruins, survivors, the long, difficult work of reconstruction and memory. What Neptune would do to Earth leaves no aftermath. It leaves no ruins. It leaves a nothing that could be recognized as the origin of something that was once here. Just blue. Just those deep, beautiful, indifferent bands of methane and hydrogen and frozen wind. Moving on. Voyager 2 is the only spacecraft humanity has ever sent to Neptune. 1. In the entire history of spaceflight, across every mission ever conceived, funded, launched, and celebrated by every space agency on Earth, exactly one probe has made the journey to the outermost confirmed planet of our solar system. It arrived on August 25, 1989. It spent approximately 6 hours in close proximity to Neptune during its flyby. 6 hours, less time than most people spend sleeping on an ordinary Tuesday night. And then it continued outward, past the ecliptic plane, past the heliopause, into the interstellar medium where it now travels in permanent, unreturning silence. 6 hours. That is the sum total of humanity's direct observational encounter with the most violent weather system in the solar system. 6 hours of data collected at hypersonic relative velocity by instruments designed in the 1970s. running on a power supply roughly equivalent to a dim household light bulb, transmitting information back to Earth at a signal so weak that it required the largest antenna arrays on the planet to detect. And yet, those 6 hours changed everything we thought we knew. Before Voyager 2 arrived at Neptune, we expected a cold, quiet, largely featureless world. The models predicted sluggish atmospheric circulation, minimal storm activity, a planet that had spent 4 billion years slowly radiating away whatever dynamic energy it had been born with. The expectation was not born from laziness or intellectual carelessness. It was born from the best physics available, from the reasonable extrapolation of solar energy input to atmospheric kinetic energy output that worked perfectly well for every other planet we had studied. Neptune destroyed those models in 6 hours. The instruments aboard Voyager 2 recorded wind velocities that the engineering team initially questioned. Not because the instruments were malfunctioning, they were performing flawlessly, but because the numbers they returned were so far outside the predicted range that the human response was disbelief before acceptance. Scientists sat with those data streams and ran the calculations again and again, and the numbers kept returning the same answer, patient and indifferent to the shock of the people reading them. 2,100 miles per hour. There is a particular quality to the moment when reality refuses to conform to your model of it. It is not simply the intellectual experience of being wrong. Being wrong is a familiar, manageable feeling, part of the normal rhythm of scientific inquiry. This was something different. This was the universe demonstrating, with quiet authority, that the confidence embedded in the prediction had been borrowed from a familiarity with conditions that simply did not apply here. It was a reminder that extrapolation has edges, that the maps we draw of the unknown are always, at their borders, more wish than knowledge. And Neptune was waiting at exactly that border, patient, windswept, and completely unconcerned with what we had expected it to be. Since 1989, we have observed Neptune exclusively from a distance. The Hubble Space Telescope has tracked the evolution of its storm systems across decades, watching dark vortices appear and disappear and reform with an unpredictability that continues to challenge atmospheric models. Ground-based observatories have refined our measurements of its wind bands, its rotational dynamics, its thermal emissions. The James Webb Space Telescope has now turned its extraordinary infrared sensitivity toward that blue world and returned images of such clarity that Neptune's ring system, a faint, narrow structure of dust and ice particles so dim it was barely detected by Voyager 2, appears with the structural definition of a photograph taken from nearby orbit. But we have not gone back. No orbiter has settled into Neptune's gravitational embrace and begun the slow, patient, years-long work of mapping its atmosphere with the resolution the science demands. No atmospheric probe has been released into those hypersonic winds to transmit data in the seconds before it is destroyed. No mission has been funded, built, and launched to close the gap between what 6 hours of flyby data told us and what decades of residency could reveal. The distance is part of the reason. Neptune sits, on average, 2.8 billion miles from Earth. At the velocities achievable by current chemical propulsion systems, a direct trajectory to Neptune requires approximately 12 years of travel time, 12 years of cruise phase, of instruments waiting in low-power hibernation, of mission teams cycling through generations of personnel, of funding cycles and political priorities shifting around a spacecraft that will not arrive within any comfortable electoral or budgetary time frame. The New Horizons mission to Pluto, launched in 2006 and arriving in 2015, required 9 years and represented one of the longest mission timelines NASA had ever sustained from launch to primary science objective. A dedicated Neptune orbiter would exceed that timeline by years, demanding institutional patience of a kind that modern funding structures are not designed to accommodate. But the distance is not only the reason. There is something else embedded in our absence from Neptune. Something that goes beyond budget cycles and launch windows and the engineering challenges of surviving a 12-year cruise phase. Something more honest and more uncomfortable. We do not fully understand what we would find there. And that uncertainty, that admission that our models are insufficient, that our extrapolations have already been humiliated once by this world and could be humiliated again, carries with it a weight that is not strictly scientific. It carries the particular discomfort of approaching something you know is beyond your current capacity to interpret, of sending instruments into an environment so extreme that designing them requires guessing at conditions you have never directly measured, building tolerances around parameters you can only estimate, and hoping that the engineering margins you have calculated are wide enough to survive contact with a reality that has already demonstrated its willingness to exceed your expectations. Neptune does not care about your margins. That is perhaps the most philosophically significant thing about it. Every other environment humanity has explored, the deep ocean trenches, the volcanic calderas, the surface of Mars, the corona of the Sun observed remotely by the Parker Solar Probe, has been approachable through some chain of incremental engineering. Each step harder than the last, each requiring new materials and new methods, but each connected by a continuous thread of achievability to what came before. Human exploration has always moved along that thread, extending it gradually, testing it carefully, never cutting entirely free of the accumulated knowledge that gave it tensile strength. Neptune asks you to cut the thread. It asks you to build something that can function in an environment where the closest analog on Earth is a hypersonic wind tunnel test lasting milliseconds, not years, where the atmospheric chemistry involves compounds that corrode instrumentation in ways that Earth-based testing cannot fully replicate, where the pressure gradients and temperature inversions and electromagnetic environment created by Neptune's powerful and poorly understood magnetic field, tilted 47 degrees from its rotational axis, offset from the planetary center in ways that suggest an interior structure unlike anything in our current models, interact in combinations we can simulate on paper, but have never verified against reality. The magnetic field alone is a mystery that should occupy a generation of scientists. Neptune's magnetosphere behaves in ways that distinguish it categorically from every other planetary magnetic field we have studied. Earth's magnetic field is generated by the convection of liquid iron in the outer core, a dynamo that aligns roughly with the rotational axis and produces a field that, while complex, follows patterns we have spent centuries learning to map. Jupiter and Saturn have magnetic fields generated by metallic hydrogen deep in their interiors, massive, powerful, but again broadly aligned with rotation in ways that make them geometrically interpretable. Neptune's magnetic field does not align with anything we would expect. It is tilted, it is offset from the center, it reverses and fluctuates in ways that suggest the dynamo generating it exists not in the deep interior, but in a conducting layer of ionic fluid at intermediate depths. A proposition that requires a fundamentally different model of how magnetic fields are generated inside ice giant planets. A model we do not yet have. We are looking at Neptune from billions of miles away. With instruments not designed for its specific environment, armed with models its atmosphere has already falsified once. And trying to understand a world that appears to operate by physical principles we can describe mathematically, but cannot yet explain from first principles. That is not a failure. That is the most precise definition of a scientific frontier that exists. And frontiers, by their nature, are places where the comfortable certainty of the known ends, and where something vast and indifferent and magnificent begins. 4.5 billion years ago, there was no Neptune. There was no solar system in any form we would recognize. There was a nebula, a slowly rotating cloud of gas and dust so vast that the light crossing it from one edge to the other would take years to complete the journey. Hydrogen, helium, traces of heavier elements forged in the cores of stars that had already lived and died before our sun existed. Carbon, oxygen, nitrogen, silicon, iron, all of it suspended in a diffuse, cold, almost imperceptibly structured fog, moving in the slow gravitational waltz that precedes collapse. Then something disturbed it. The leading hypothesis is a nearby supernova, a massive star ending its life in a detonation so energetic that it briefly outshone entire galaxies, sending a shockwave through the surrounding interstellar medium that compressed the nebula past the threshold of gravitational stability. The cloud began to fall inward, slowly at first, then faster. Conservation of angular momentum, the same physical law that causes a spinning ice skater to accelerate when they pull their arms inward, transformed that gentle rotation into a progressively faster spin as material collapsed toward the center. The center became the sun. The outer regions, the flattened disk of remaining gas and dust that formed around the young star as it ignited, became everything else. Planets accreted from that disk through a process of collision and accumulation that is violent beyond easy description. Not the orderly, peaceful assembly the word accretion implies, but billions of years of objects slamming into each other at velocities measured in miles per second, merging and fracturing and remerging, gradually building larger and larger bodies from the accumulated wreckage of smaller ones. Earth formed from this process in the inner solar system, where temperatures were high enough that only rock and metal could condense. The volatile compounds, the ices, the gases, were driven outward by the young sun's radiation pressure into the colder regions of the disk. Neptune formed out there, in the cold. But here is where the story diverges from the clean, orderly version we prefer to tell. Neptune almost certainly did not form where it currently orbits. The models of planetary formation that produce a solar system resembling our own require the ice giants, Uranus and Neptune, to have formed much closer to the Sun than their current positions, in a region where the density of the protoplanetary disk was high enough to supply the material for their formation within the time constraints imposed by the young sun's evolution. The disk did not survive long enough to build ice giants at 4 billion miles from the Sun. The material was too sparse, the collision rates too low, the time scale too extended. Neptune formed closer in, and then it moved. The mechanism is gravitational interaction with Jupiter and Saturn, the two gas giants whose combined mass dominates the solar system's dynamics, the way a pair of enormous spinning gyroscopes dominate the motion of everything near them. In the early solar system, as Jupiter and Saturn settled into a temporary orbital resonance, the gravitational consequences rippled outward through the disk, like a shock wave through still water. Uranus and Neptune were captured in that ripple and flung outward. Not violently, not in the span of a human lifetime or even a geological epoch, but over millions of years of incremental gravitational nudging that eventually deposited them in the outer solar system where they reside today. This migration was not gentle for the solar system it passed through. As Neptune moved outward, it swept through the primordial belt of planetesimals, the small, icy bodies that populated the outer disk in numbers that dwarf anything remaining today. Neptune's gravitational field captured some of them into resonant orbits, creating the populations of trans-Neptunian objects we observe in the Kuiper Belt today. It scattered others inward, sending a bombardment of icy projectiles toward the inner solar system in an event planetary scientists call the Late Heavy Bombardment, a period approximately 4 billion years ago when the impact rate on Earth, the Moon, Mars, and every inner planet spiked dramatically. Those impacts are recorded in the lunar surface. Every large crater you see when you look at the Moon on a clear night, every ancient, overlapping basin and ray system that gives the lunar face its battered, scarred appearance, is, in part, a consequence of Neptune moving outward through the solar system. The Moon is a fossil record of Neptune's migration, written in impact craters across a surface that has preserved them for 4 billion years in the absence of weather and erosion. Neptune moved through the solar system and left its signature on our Moon. Consider the intimacy of that connection. The world with the most violent winds in the solar system, the world that would destroy Earth's atmosphere in hours and reduce its oceans to vapor, is also the world whose gravitational history shaped the face of the Moon you have looked at every night of your life. The same migration that bombarded the early Earth with icy projectiles, possibly delivering some portion of the water now filling Earth's oceans and the organic molecules that seeded the chemistry of life. That same migration eventually deposited Neptune at its current distance and left it there, spinning, radiating internal heat, driving hypersonic winds across its cloud bands in the permanent darkness of the outer solar system. We may owe some part of our existence to Neptune's journey, and Neptune, utterly indifferent, has spent the last 4 billion years trying to tear apart everything that existence produced. There is a philosophical tradition, ancient, persistent, appearing independently across cultures that never communicated with each other, that frames the universe as fundamentally indifferent to human existence, not hostile, not benevolent, simply operational, running according to principles that predate life, that will outlast life, that have no more awareness of life's presence than a river has awareness of the pebbles it carries. Neptune is the purest physical embodiment of that tradition that exists within reach of human observation. It is not trying to destroy. It has no intent, no agenda. The winds do not blow with malice. They blow because heat rises, because rotation deflects, because pressure seeks equilibrium in a system so large and so friction-free that equilibrium is never reached and the seeking never ends. The destruction those winds would visit upon anything fragile enough to enter their path is not violence in any meaningful sense. It is simply physics, operating at a scale that overwhelms the structures biology and geology and human engineering have produced. The wind does not know you exist. And somehow that is more terrifying than if it did, because malice can be negotiated with, outwitted, survived through cleverness or endurance or the particular human stubbornness that has carried our species through ice ages and plagues and the full catalog of disasters this planet has produced. Malice has a psychology, and psychology has vulnerabilities, and vulnerabilities can be exploited by minds sharp enough to find them. Indifference has no vulnerabilities. You cannot outwit a pressure gradient. You cannot negotiate with angular momentum. You cannot appeal to the mercy of a planetary atmosphere that has been running the same hypersonic program for 4 billion years without once pausing to consider whether what it is doing is appropriate. Neptune's winds were blowing before the first photosynthetic bacterium changed the chemical composition of Earth's atmosphere. They were blowing when the first fish pulled itself onto land. They were blowing through the entire Mesozoic era, 200 million years of dinosaurs and ferns and shallow inland seas. Without interruption, without variation in any direction that matters to life, without the slightest acknowledgement that something remarkable was happening on the third rock from the sun, they are blowing right now, at this exact moment, as you process these words. As the neurons in your brain fire in the electrochemical patterns that constitute understanding. 4 billion miles from the chair you are sitting in, hypersonic rivers of frozen methane and hydrogen are tearing across the face of a blue giant with a violence so absolute and so sustained that human language genuinely struggles to carry its weight. Right now, not in the past, not in some distant future scenario. Now, the wind that would end Earth in minutes has been blowing continuously for longer than complex life has existed on this planet. And it will continue blowing long after the last trace of our civilization has been absorbed back into the geological record and forgotten by a universe that never noticed it was there. That is not a reason for despair. It is a reason for precision, for paying very careful attention to exactly what we are, and exactly where we are, and exactly how extraordinary it is that we are capable of knowing any of this at all. We end where we must always end. Here, not on Neptune, not in the cold mathematics of hypersonic wind speeds and dynamic pressure calculations and the slow gravitational migrations of a solar system assembling itself from the wreckage of dead stars. Here, on this precise, improbable, heartbreakingly thin margin of conditions that permits something as delicate as a living mind to exist and to ask questions about the universe that produced it. The average wind speed on Earth's surface is approximately 7 miles per hour. 7, not 2,100. Not the supersonic fury of atmospheric bands, unrestrained by friction or geography or any of the thousand small resistances that bleed energy from moving air before it can accumulate into something lethal. 7 miles per hour. A gentle, almost apologetic movement of atmosphere that you feel as a mild coolness against your skin, that rustles leaves and moves clouds and carries the smell of rain before it arrives. A force so modest that children run through it laughing without losing their footing. 7 miles per hour is the wind speed of a living planet. 2,100 miles per hour is the wind speed of a planet that has never been asked to accommodate life and has never once adjusted itself in that direction. The difference between those two numbers, that factor of 300 that separates Earth's ambient atmosphere from Neptune's ambient destruction, is not random. It is not coincidence. It is the product of a specific constellation of physical circumstances so precisely configured that the probability of their simultaneous occurrence, even within a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, remains a number that humbles every attempt to calculate it with confidence. Earth is the right distance from the right kind of star, not so close that solar radiation strips the atmosphere away, as it stripped Mars bare over billions of years once the Martian magnetic field weakened and left its atmosphere unprotected against the solar wind. Not so far that the energy reaching the surface is insufficient to drive the liquid water cycle. That extraordinary, planet-spanning engine of evaporation and precipitation and river flow that has been redistributing heat and chemistry across this world for 4 billion years. Earth has a large moon, an absurdly large moon, relative to the size of the planet it orbits. A moon so massive in proportion that the Earth-Moon system is sometimes described as a double planet rather than a planet with a satellite. That moon stabilizes Earth's axial tilt. Without it, the gravitational perturbations of Jupiter and the other planets would cause Earth's rotational axis to wander chaotically over timescales of millions of years, producing climate variations so extreme and so unpredictable that the long, stable epochs required for complex life to evolve from chemistry to consciousness may never have materialized. The moon holds Earth steady. And the moon exists because approximately 4.5 billion years ago, a Mars-sized protoplanet named Theia struck the young Earth in a collision of such violence that it partially vaporized both bodies, ejecting a ring of molten rock and metal into Earth's orbit that eventually coalesced into the satellite we have looked at and navigated by and written poetry about for the entire history of our species. We have a stable climate because a protoplanet crashed into us at the dawn of the solar system. Earth has plate tectonics, the slow, grinding movement of crustal plates driven by internal heat that recycles carbon from the atmosphere into rock and back again over geological timescales, maintaining the carbon cycle that regulates atmospheric composition and prevents the runaway greenhouse heating that transformed Venus from a potentially habitable world into a hellscape of sulfuric acid clouds and surface temperatures hot enough to melt lead. Earth has a magnetic field strong enough and well-aligned enough to deflect the solar wind. That constant stream of charged particles flowing outward from the sun that would, over geological time, erode an unprotected atmosphere the way Neptune's winds would erode ours in hours, just more slowly, more patiently, with the quiet persistence of a process that does not need to hurry because it has billions of years to work. Every one of these conditions, the orbital distance, the lunar stabilizer, the tectonic carbon cycle, the magnetic shield, the size and composition of the planet itself, had to be present simultaneously. Remove any single one and the cascade of consequences propagates through the system until the margin that permits life collapses. And sitting 4 billion miles away from all of it, Neptune reminds us what a planet looks like when that margin is absent. Not a failed planet, not a broken planet. A planet operating exactly as physics permits it to operate under its specific set of initial conditions. More massive than Earth, farther from the sun, formed in the cold outer disk where volatile compounds could condense in abundance, endowed with internal heat that has not yet finished driving its atmosphere into hypersonic motion. Neptune is not the exception. Neptune is the rule. When astronomers survey exoplanets, the planets orbiting other stars, now numbering in the thousands of confirmed detections, the distribution of planetary types they find is heavily weighted toward objects resembling Neptune and its ice giant siblings. Small, rocky, temperate worlds like Earth are detected, but they are not the dominant product of planetary formation across the galaxy. The universe, given the freedom to assemble planets from available materials under available conditions, produces Neptune-class worlds with a frequency that suggests they are the natural outcome of the process, the expected result of the physics, not the anomaly. Earth is the anomaly. We are the rare configuration, the unlikely arrangement, the precise, fragile, almost statistically offensive exception to what the universe normally produces when it builds planets. And we almost missed knowing this. For the entire span of human civilization, the 10,000 years from the first agricultural settlements in Mesopotamia to the first radio telescope pointed at the sky, we had no way of knowing what lay beyond the boundary of our own atmosphere. The universe existed at a distance that precluded direct knowledge, accessible only through the light that reached us and the stories we constructed from it. We named the planets after gods, because gods were the most powerful things we could imagine, and the moving lights in the night sky demanded explanations commensurate with their strangeness. We gave Neptune the name of the god of the sea. It is the most accidentally accurate thing we have ever done, because Neptune's atmosphere behaves exactly the way the ancient mythological sea was imagined to behave. Vast beyond comprehension, indifferent to human survival, beautiful from the shore and lethal upon entry, operating according to its own internal logic that predates human existence and will outlast it without registering the interval. The god of the sea did not notice the ships it sank. Neptune does not notice us, but we notice Neptune and that asymmetry, that extraordinary, improbable fact that the fragile arrangement of matter on this small, warm rock has produced minds capable of measuring the wind speed of a world 4 billion miles away, of calculating the dynamic pressure those winds would exert on a human body, of tracing the gravitational history that moved Neptune outward through the solar system and left its signature in craters on our moon. That asymmetry is the most remarkable thing in this entire story, not the winds, us. The winds are physics. They are the inevitable output of mass and heat and rotation operating without constraint across a timescale that dwarfs human comprehension. There is nothing surprising about them once you accept the initial conditions. Given Neptune's composition, its internal heat, its distance from the sun, its size, its lack of surface friction, the winds follow. They are compulsory. The universe had no choice but to produce them. We were not compulsory. Nowhere in the laws of physics is there a requirement that matter must eventually arrange itself into forms capable of curiosity. Nowhere in the equations governing planetary formation is there a term that demands the emergence of consciousness. The universe could have run its entire history, its full 13.8 billion years from the first fraction of a second after the Big Bang to the cold, dark, and tropic endpoint that awaits it, without ever producing a single mind to observe it. It did not have to make something that wonders. And yet, here we are, wondering, sitting on a 7-mile-per-hour planet in a solar system that also contains 2,100 miles per hour, measuring both, understanding both, feeling the appropriate terror at one and the appropriate gratitude for the other, and finding in that contrast not despair, but something closer to its opposite. The wind on Neptune will outlast everything we have built, every monument, every archive, every signal we have sent into space, carrying the compressed record of our music and mathematics and languages and longing. All of it will end before Neptune's winds pause for even a fraction of a second. But for now, right now, in this sliver of cosmic time we have been given, we are here, breathing 7-mile-per-hour air, warm, alive, knowing, and knowing is everything.